This machine has been generating electricity since before the moon landing. It doesn't burn anything. It doesn't spin a turbine. It runs on a bath of molten salt heated to 1,200 degrees Fahrenheit, and it's been quietly powering breweries, submarine bases, and entire Korean towns for over 2 decades. Yet the company that invented it has lost 97% of its stock value, been forced through 2 separate reverse stock splits just to stay listed on NASDAQ, gotten dragged through an international arbitration battle worth hundreds of millions of dollars, and still hasn't turned a profit in over 50 years of trying. It's called a molten carbonate fuel cell. By the end of this video, you'll know exactly how it works, where it's actually running right now, and why a technology this proven has had such a brutal time turning into a real business. Let's dive in. If you run a business with serious power needs, a brewery, a hospital, a military base, a manufacturing plant, you already know the grid isn't built for you. Commercial electricity rates have climbed steadily for years, and a single outage can cost a facility more in spoiled inventory and downtime than a full year of power bills combined. Diesel generators are loud, dirty, and never meant to run continuously. Solar helps on paper, but it can't carry a facility that operates 24 hours a day, and it does almost nothing for you the moment the grid actually goes down, because most solar systems are legally required to disconnect during an outage to protect utility line workers. What operations like these actually need is baseload power, electricity made on site, around the clock, that doesn't care whether the sun is shining or the grid is up. That is precisely the promise behind this technology, and unlike most clean energy solutions you hear about, it's been proven at industrial scale since before most of us were born. The company behind it is called Fuel Cell Energy, and its story starts almost 60 years ago, long before clean energy was even a phrase people used. In 1969, a chemical engineer named Bernard Baker founded a company called Energy Research Corporation in Connecticut. Baker had trained under a Dutch electrochemist named G.H.J. Brouwers at the University of Amsterdam, a man fixated on one very specific problem. Every fuel cell of that era needed a separate device called a reformer, just to strip hydrogen out of a fuel like natural gas before the fuel cell could even use it. That extra step added cost, added complexity, and added another point of failure. Brouwers wanted the fuel cell to do that reforming itself internally, with no external device required. That single idea became the foundation of the molten carbonate fuel cell, and Baker spent the rest of his career trying to turn it into a real, sellable product. Here's how it actually functions. Picture a shallow bath of molten salt, a mixture of lithium and potassium carbonate, held inside a porous ceramic matrix and heated until it liquefies, somewhere around 650 degrees Celsius, or roughly 1,200 degrees Fahrenheit. That molten salt becomes the electrolyte. Natural gas flows in on one side of the cell, and a nickel catalyst built directly into the stack reforms it into hydrogen right there, with no external reformer required. Carbonate ions then carry the electric charge from the air side of the cell through to the fuel side, and that movement of ions is what generates electricity. No combustion, no flame, no spinning turbine anywhere in the system. If you've ever seen a chemistry set left permanently on a slow, controlled boil, that's a decent picture of what's happening inside the stack, just contained, engineered, and turned into usable power instead of a science fair demonstration. Baker's company spent its first decade bouncing between battery research and fuel cell contracts, chasing whatever government funding it could find, because in the 1970s, nobody was writing checks for commercial fuel cells. In the early 80s, the company committed fully to molten carbonate technology as its flagship product, betting the entire business on a chemistry that hadn't been proven outside a lab. It went public in 1992. It reincorporated in Delaware in 1999 and renamed itself Fuel Cell Energy. And in 2003, after more than 3 decades of research, it sold its very first commercial power plant. Not to a tech giant, not to a government lab, to the Kirin Ichiban Brewery in Tokyo, running on biogas too. Produce carbon-neutral electricity and steam for the brewing process. That single installation has now been quietly running for over 20 years, brewing beer with electricity, made from a chemical reaction instead of a flame. That patience, 34 years from founding to first commercial sale, tells you almost everything you need to know about this company's entire history. The technology works. Getting it out the door and into paying customers has always been the hard part. Take the U.S. Navy submarine base in Groton, Connecticut. This project was first announced back in May of 2017, a plan to install two SureSource 4,000 power plants generating a combined 7.4 megawatts, enough to supply an existing electrical substation for the Connecticut Municipal Electric Energy Cooperative and add real resiliency to a facility the Navy considers strategically important. If there's ever a regional blackout, this fuel cell park alone can meet the entire base's critical load on its own. Officials broke ground on the project in the summer of 2018. Financing came together in pieces over the following years, a $23 million construction facility from Fifth Third Bank in 2019. Additional financing from the Connecticut Green Bank that same December, another $15 million tax equity deal with East West Bank in 2021. Power plant deliveries didn't begin until January of 2020, and the project didn't actually reach commercial operation until December 16th of 2022, running at around 6 megawatts, with the plan to hit the full 7.4 megawatts by the end of that year. From announcement to full commercial power, this project took the better part of 6 years. 6 years for a facility built on less than an acre of land next to a substation that already existed. That's not a technology problem. Molten carbonate fuel cells don't need 6 years to prove they work. That's a company that has repeatedly struggled to move projects from paper to power quickly, and it's a pattern that shows up again and again across its history. Now compare that to a project that actually moved fast, because fuel cell energy has pulled it off before. In 2023, the company completed something called the Tri-Gen system at the Port of Long Beach, built to serve Toyota's largest vehicle processing facility in North America, a site that handles roughly 200,000 new Toyota and Lexus vehicles every year. Tri-Gen runs entirely on biogas and does 3 things simultaneously, which is where the name comes from. It generates about 2.3 megawatts of renewable electricity. It produces up to 1,200 kilograms of renewable hydrogen every single day, enough to fuel both light-duty Mirai vehicles and heavy-duty hydrogen trucks moving cargo through the port. And it produces roughly 1,400 gallons of usable water daily as a byproduct of the hydrogen production process, cutting the facility's demand on local water supplies by nearly 500,000 gallons a year. Toyota signed a 20-year agreement to purchase everything the system makes. Whatever electricity Toyota doesn't use on site gets sold back to Southern California Edison, adding enough surplus power to the grid to supply almost 2,500 homes in the neighborhoods around the port. It's the first facility of its kind anywhere in the world, 3 separate outputs from one electrochemical process, and it's projected to help avoid more than 9,000 tons of carbon dioxide emissions every year. When this company executes well, it genuinely delivers something nobody else on Earth has built. But the project that probably tells you the most about this company isn't in Connecticut or California. It's in South Korea. In 2007, Fuel Cell Energy signed a licensing deal with a company called POSCO Energy, part of the massive Korean steel conglomerate POSCO. POSCO Energy paid an initial $29 million just to secure exclusive rights to assemble, market, and service Fuel Cell Energy's molten carbonate technology across South Korea and the rest of Southeast Asia. Later, POSCO Energy invested another $55 million on top of that. For a while, this partnership looked like exactly the kind of scaling deal a small American technology company dreams about. Access to Asian manufacturing, Asian capital, and an entire continent of potential customers. Installations under this partnership eventually powered facilities like the Gyeonggi Green Energy Park, a site generating 59 megawatts of electricity, plus district heating for the surrounding community, one of the largest fuel cell installations on the planet at the time. Then, in November of 2019, POSCO Energy spun off its fuel cell business into a new separate company called Korea Fuel Cell Company, without Fuel Cell Energy's consent, transferring manufacturing and service rights to the new entity, while POSCO itself walked away from liability under the original agreements. Fuel Cell Energy formally objected. Then, in April of 2020, POSCO Energy filed a series of arbitration demands, alleging warranty defects and seeking damages that eventually eventually totaled roughly $800 million. Fuel Cell Energy countersued, seeking $200 million of its own and the termination of the entire licensing agreement. For over a year, the two companies fought this out through parallel arbitration proceedings in London and Singapore. While Korean courts froze millions of dollars in revenue Fuel Cell Energy was owed from a separate Korean power company, delaying payments the business badly needed. It wasn't until late 2021 that the two sides finally reached a settlement, one that restored Fuel Cell Energy's exclusive rights to the Korean and broader Asian market, while allowing POSCO to keep servicing the customers it already had. The company had spent the better part of 2 years locked in expensive international litigation over a partnership that was supposed to be its growth engine in Asia. And through all of this, Fuel Cell Energy was also quietly working on something that might matter more long-term than any single power plant. Starting in 2016, the company began a joint development agreement with ExxonMobil's research division, exploring whether molten carbonate fuel cells could do something genuinely different, capture carbon dioxide directly out of a power plant's exhaust while generating additional electricity at the same time, instead of burning extra energy the way traditional carbon capture does. Most carbon capture technology works by passing exhaust through a chemical solution that absorbs CO2, then heating that solution to release the captured gas again, a process that can eat up around 17% of a power plant's total output just to run the capture system. Fuel Cell Energy's approach flips that math. The molten carbonate itself does double duty, generating power from natural gas while simultaneously concentrating carbon dioxide out of an external exhaust stream running through the cell. In 2019, that research turned into a formal license agreement with ExxonMobil for what the company calls its SureSource capture product. By 2022, the two companies had extended their joint development agreement multiple times, with ExxonMobil agreeing to reimburse up to $60 million in research costs, working toward a demonstration project at an ExxonMobil facility in Rotterdam. It's a genuinely interesting pivot, using 50-year-old chemistry to solve one of the newest problems in the entire energy industry. Whether it ever becomes a meaningful revenue source is still an open question. And that brings us to the number that explains everything else about this company. In the most recent 12 months on record, Fuel Cell Energy brought in about $170 million in revenue and lost close to $186 million doing it. The company spent more money losing money than it made selling its own product. And this isn't a rough patch. This has been the pattern for essentially the company's entire existence as a publicly traded business, stretching back to 1992. Over 3 decades of quarterly earnings calls and profitability has remained permanently a few years away. To keep operating through all of that, Fuel Cell Energy has repeatedly issued new shares of stock to raise cash, diluting existing shareholders again and again. That approach works right up until the stock price collapses under the weight of all that new supply, and it did more than once. Shares fell so far that the company needed a reverse stock split in December of 2015. Folding 12 old shares into one just to stay above NASDAQ's minimum listing price of $1. That bought time. It didn't fix anything underneath. By 2024, the stock had cratered again, down as much as 97% from its highs, forcing a second reverse split, this time consolidating 30 old shares into one, shrinking more than 600 million shares outstanding, down to roughly 20 million overnight. One shareholder, writing in a public filing opposing the move, called it death by 1,000 cuts for anyone who had believed in the company's technology. The board urged shareholders to approve it anyway, framing it as necessary for NASDAQ compliance rather than a referendum on strategy. It passed. The stock still trades for a fraction of what long-term holders originally paid. So how does a company invent a genuinely working, genuinely scalable clean energy technology, hold over 500 patents on it, install it in breweries, submarine bases, and industrial ports across 3 continents, and still never manage to turn a profit? Part of the answer is cost. Molten carbonate stacks are complex and expensive to manufacture at the volumes needed to bring the price down, and the company has spent decades trying to hit that scale while competing against subsidized natural gas power and, more recently, against heavily subsidized solar and battery storage. Part of the answer is execution speed, as the 6-year timeline on the Groton Submarine Base project shows. And part of the answer is exactly what happened with POSCO Energy, a company that bet its international growth on a single overseas partner, only to spend 2 years in untold legal fees fighting that same partner in arbitration instead of installing new power plants. If you're a business owner actually evaluating on-site power generation today, this history matters more than the spec sheet. A 20-year power purchase agreement, like the one Toyota signed at the Port of Long Beach, is only as good as the company standing behind it 2 decades from now. Ask about the balance sheet, not just the megawatts. Ask about the company's track record on project timelines, not just the brochure. Ask who services the stack if the manufacturer needs to restructure. The molten carbonate fuel cell itself isn't the risk here. It's been running without a major technical failure at the Kirin Brewery in Tokyo for over 20 years, and it's currently supplying power to a United States Navy submarine base. The risk sitting underneath all of that proven engineering is entirely financial, and it's worth understanding in detail before anyone signs a contract measured in decades. Here's what this comes down to. Fuel cell energy built an entire industry out of a bath of molten salt and a nickel catalyst, sold the first commercial unit of its kind in the world back in 2003, and is still running plants in Connecticut, California, and South Korea, generating carbon-neutral power right now, today, more than 50 years after Bernard Baker founded the company on a bet about internal reforming. And despite every one of those real working installations, it remains one of the most financially bruised names in clean energy, a company that has had to shrink its own share count by a factor of 30 just to keep its stock ticker on the board. The lesson here isn't really about chemistry. It's about what happens to genuinely good, genuinely proven technology when the business behind it spends half a century struggling to turn invention into consistent profit. So here's the question. If a facility near you offered to sell you power from a molten carbonate fuel cell running on natural gas or biogas at a fixed rate for the next 20 years, backed by a company with this exact financial and legal history, would you sign that contract? Or would you walk straight past it toward a competitor with a shorter track record but a stronger balance sheet? Drop your answer in the comments because I have a feeling the split on this one is going to surprise you. And here's a number to sit with before you go. Fuel cell energy holds over 500 patents on technology that generates carbon-free base load power from a chemical reaction discovered more than 50 years ago. Technology proven enough that the United States Navy trusts it to keep a submarine base running during a blackout. That's how good the engineering actually is. The story here was never about whether the science works. It's about how much harder it is to build a lasting business than it is to build a working machine. If this kind of buried in plain sight technology matters to you, subscribing and sharing is the single best way to make sure it keeps getting found. And if you want to see how a technology this old almost disappeared completely before one engineer refused to let it die, that story is up next.